It began like any other quiet morning in deep space, far beyond the orbit of Mars, beyond the drifting rocks of the asteroid belt, beyond the comfortable warmth of the inner solar system. Something impossible appeared on the screens of astronomers around the world. Saturn was no longer golden. It was white, not pale, not slightly brighter than usual, completely white. Its soft yellow glow had vanished. The familiar cloud bands were gone. Even its vast rings, normally shimmering with icy brilliance, reflected sunlight like polished glass. At first, scientists assumed it was a malfunction, a calibration error, a corrupted feed from orbiting telescopes. But observatories across different continents confirmed the same image. The gas giant had changed, and no one knew why. To understand what that meant, we have to remember what Saturn is supposed to look like. For centuries, Saturn has been the pale jewel of our solar system. Through ground-based telescopes and the close observations of the Cassini-Huygens mission, we've seen its muted golden atmosphere, wrapped in delicate bands and crowned with rings made mostly of water ice. But Saturn is not truly yellow. Its color is a result of chemistry and light. High above the crushing depths of the planet float clouds of ammonia ice. Beneath them lie layers of ammonium hydrosulfide and deeper water clouds, all stirred by violent winds. Sunlight travels nearly 1.4 billion kilometers to reach Saturn. When that light strikes its atmosphere, different wavelengths scatter in different ways. The upper haze filters the light, giving Saturn its soft golden tone. The planet is not painted, it is illuminated. Its color is physics in motion. So if Saturn appeared white, something in that delicate balance must have shifted. When something changes in the outer solar system, scientists first look to the sun. Solar flares and coronal mass ejections can hurl enormous waves of charged particles into space. On Earth, such storms can disrupt satellites and power grids. If a powerful eruption had recently exploded from the sun, perhaps it could have altered Saturn's upper atmosphere, stripping haze or triggering chemical reactions that changed how light reflects off the clouds. It was a reasonable theory, but Saturn has a powerful magnetic field, far stronger than Earth's. Its magnetosphere forms a massive shield that deflects most incoming solar radiation. For the sun to bleach an entire planet's atmosphere, the storm would have to be unlike anything humanity has ever recorded, and no such eruption had been detected. The sun was active, but not that active. Then scientists noticed something else. The rings were brighter too. Saturn's rings are made largely of water ice, and ice reflects sunlight extremely well. But now their reflectivity readings were off the charts. Shadows seemed to fade. Subtle grey tones between ring divisions nearly disappeared. It was as if every fragment of ice had been polished at once. For the rings to blaze that intensely, either the light reaching them had changed, or Saturn itself was amplifying that light, acting like a colossal reflector. The planet and its rings were responding together. Whatever was happening was not isolated. It was system-wide. There is something most people do not realize about Saturn. It looks calm from a distance, but it is not calm. Roughly once every Saturnian year, which lasts about 29 Earth years, the planet unleashes enormous storms. One of the most dramatic is known as the Great White Spot, a massive system that can grow large enough to wrap around the entire planet. During the Cassini mission, scientists observed one such storm erupt and spread with astonishing speed. Lightning flashed inside towering clouds. Winds roared faster than the strongest hurricanes on Earth. These megastorms dredge material from deep within the atmosphere, pulling ammonia and water vapor upward where they freeze into bright ice crystals. More ice means more reflection. More reflection means more brightness. So what if, this time, the storm did not stop? What if instead of forming a single band, it spread across the entire globe? A complete atmospheric upheaval. Deeper layers exposed, the upper atmosphere saturated with reflective ice. It could explain the disappearance of color, but even Saturn's greatest storms eventually fade. They do not usually erase an entire planet's identity overnight, unless something deeper is involved. Gas giants do not shine only because of the sun. Saturn actually produces more heat than it receives. Deep inside, gravity slowly compresses hydrogen and helium, releasing energy that rises upward and drives convection currents. Warm gases ascend, cooler gases sink. This internal heat engine has been running for billions of years. If that balance were disturbed, even slightly, the consequences could ripple upward. A cooler upper atmosphere would cause gases like ammonia to condense more readily into ice crystals. High altitude haze could thin or collapse, replaced by dense, reflective cloud layers. Without the yellowish photochemical smog filtering the light, sunlight would bounce more cleanly off the upper clouds. The planet would appear whiter, brighter, almost stripped of personality. But perhaps the most elegant explanation lies not in catastrophe, but in time. Saturn takes nearly 29 Earth years to orbit the Sun. Its axis is tilted, just like Earth's, which means it experiences seasons. Each season lasts more than 7 Earth years. As Saturn moves along its orbit, sunlight strikes different hemispheres at changing angles. Temperature gradients shift, wind systems reorganize, chemical reactions in the upper atmosphere strengthen or weaken, depending on solar exposure. Over time, the very haze that gives Saturn its golden appearance can thin. When that haze clears, the deeper ammonia ice clouds become more visible, and ammonia ice is highly reflective. Historical observations have shown that Saturn's brightness varies over decades, especially near seasonal transitions. What looks like a sudden transformation may actually be a slow reveal. Saturn may not have turned white overnight. We may simply have witnessed one of its long, subtle atmospheric cycles reaching a visible peak. And if that were true, Earth would have nothing to fear. Saturn lies far too distant to disturb our orbit or climate. But scientifically, such a change would remind us of something profound. Gas giants are not static ornaments in the sky. They are dynamic worlds of motion and chemistry. Jupiter has changed in color and storm intensity over time. Neptune's storms have appeared and vanished within years. Planetary atmospheres evolve continuously, even if those changes unfold more slowly than a human lifetime. What we call normal is only a snapshot. In the end, Saturn turning white would not mark a disaster. It would mark a lesson that permanence in the cosmos is often an illusion, that even giants change. Somewhere tonight, Saturn still hangs in the darkness, distant and quiet. Whether golden or pale, it continues its slow journey around the Sun, storms churning beneath layers of ice and haze. The day it appeared white would not be the day it became something new. It would be the day we realized it was never standing still at all.